So here we have the part integral of 24th May 2026. Alright, I've isolated the integral here so it's a bit easier to see. So seeing this expression, I immediately suspected an integration by parts. So we differentiate the inverse tangent and integrate the x of n. So once we do that, we should get these terms, these functions, and let's multiply those together, which will give us these two terms. And let's simplify this expression. Yeah, okay, so this should give us 1 over n plus 1 times power 4 in the first term. Let's further factor out 1 over n plus 1 to just simplifies. Okay, now we have this integral. So how do we tackle this? Well, we can try to use polynomial long division, since we know for most of the time x to the power of n plus 1 should be larger than x squared in the denominator, which we can use to our advantage and simply apply polynomial long division to simplify the integrand and make the function more manageable. So for polynomial long division, we should also know that all the other terms produced by the division itself, i.e. the quotients, should be rational, and only the fraction that remains in the integrand is irrational. So that will be our focus. Now let's look at what happens to the remainder when n has different parities. So the first case is when n is even, this fraction will integrate to a ln function. However, this will likely not cancel out with the power of 4 term. So hence we should reject this case, since the resulting integral will not be rational, and that's not what we're looking for. Next, if n is odd, then the fraction of the n should integrate to 1 over 1 plus x squared, which should integrate to inverse tangent of x. So is that it? Is the answer 50? Well, actually, no. We also need to take note of what happens to the coefficients of the quotient as we go down the division. So here I will demonstrate the example of dividing x to the power of n plus 1 by x squared plus 1. So you have your first term of the quotient, x to the power of n minus 1, since you're minusing each term by 2, subtracting each term by 2. Now you have negative x to the power of n minus 1 as your remainder. So we continue dividing. Yeah, now you have negative x to the power of n minus 3. Okay, let's continue with division. Now you have x to the power of n minus 3 as your remainder. So now you add x to the power of n minus 5 into the quotient. So that's your remainder. And we keep on going like this. Now notice the coefficients in the quotient. They are alternating. Let's go from positive in the first term to negative in the second term, positive in the third term, yeah, and so on. So the desired I of n that we want here is the one that has a positive coefficient inside the integral, so that these two terms, they will cancel out. That's what we're looking for. Yeah. So this is the I of n that we want, so that it is a rational value, a rational number. Now let's look at what conditions will give us that. The division should produce an even number of rational terms so that the final remainder will give a positive coefficient. So that will only happen when n plus 1 leaves a remainder of 0 when divided by 4. That's another condition. So after taking into account all the cases, and we should be able to find what n fulfills the conditions that we need. There are 25 numbers that satisfy such conditions, so our answer is 25. Thanks for watching.